Okay, we have covered diffusion mechanism. There are two. One is substitution mechanism, or another one is called interstitial diffusion mechanism. We will look into atomic diffusion in solid. Now we look into steady state diffusion. Steady state diffusion means we have a controlled diffusion. So if you look at the graph on the top, you have concentration C versus distance. So as x1 at distant 1, you have concentration 1, and x2 at position number 2, distant x, you have concentration drop to second concentration. Just now, in the beginning, we talked about diffusion, and you see there's between the copper and nickel. Is it copper nickel? Cu and I. So the two, and then you see the graph drop, right? So in this case, we have a steady state, mean we assume the diffusions happen in a linear motion. Just now you see a curve, but now we in the steady state, we see there's a drop of concentration from C1 to C2. Okay, then on the bottom one, is that you have a diffusion atom move between to the left or right, right, and the net flow atom per unit area you given in the joule. So this is the example of hydrogen diffusing through a metafoil, a foil. Okay. So the rest you read from the screen. So when we talk about steady state diffusion condition means that there is no change in concentration in the solid atom at this plane for the system with time. Okay. This one we'll look into tutorial question later. As you read, then the flux is given by one calculation called J equal second equation for today. J is a flux or flow of atoms represented by this equation. D is diffusibility or atomic conductivity or diffusion coefficient. The higher number D means the more easier it can mix or move into the position, right? Then C divided by X, or differential of your C towards X, is your concentration gradient. On the screen there, you are seeing a linear line, which is give you Y equal to mx plus C. When you want to find the gradient, you take delta Y divided by delta X. In this case, your delta Y is your concentration. Your X is the distant X here, right? Y negative, the negative sign is used because the diffusion happened from high to lower concentration. It moved from like a pressure principle, it moved from high pressure to low pressure. So it moved from high density into low density, high concentration into low concentration. So that's why you use a negative sign there. And the line, the straight line in steady state here is slanted. It's a negative gradient. You have a negative gradient there. This equation also called Fick's law. Fick's law of diffusion. So when the question mentioned by using Fick's law of diffusion means we expected you to write this equation out and use this equation for calculation. So I break using dimension analysis. You have learned dimension analysis? Yes? No? No. Okay. But anyway, the J is in atom over meter square second. D is in meter square over second. C is in C, the C concentration is atom over meter cube. How many atom you have in that meter cube? X is distance, meter. Okay. So this is at least you know what are the value you should use later. So these are another chart that we'll see when you talk about diffusion between the metals. So on the left is your solute. On the right is solvent. What I mean by solute and solvent? Water and salt. You put a salt inside water, the salt will be solute, water will be solvent in the host. Okay, so when you put carbon inside a FCC element, the diffusibility, there are two rows, one is in 500, one is in 1000 Celsius. Different temperature, different diffusibility. So lower temperature is minus 15. 100 degrees C, more energy will increase a little bit. 10 power negative 11. This one is minus 15. Okay, it actually increase, increase, diffusibility increase. And so on, same like this others. So these are the factor why the diffusibility value is important and how what affect the value that you see on the table here. First, the type of mechanism. It can be either interstitial or substitutional. Just now we introduced you these two mechanisms, right? So this one will fall into section A of most of the question. Ask you to explain or define diffusion. Right? Okay. The type of diffusion, the first one. For example, interstitial one, carbon in the BCC, and copper one is substitutional into aluminium. How you know which one is which one? Referring to atomic radius R. This one you learn in chapter 3 or chapter 2 when you learn about BCC, FCC. Okay, if the R of the solute is near to the solution, this one is substitutional. If the R is smaller, then it becomes interstational. Means it can go inside the space. Okay, there are two mechanisms. From the value of your R, you should able to explain what type of mechanism that happening when you do strengthening procedure later. You look at the material, you look at solute and solvent, solute and solution. Then there will be a one table before this I show you in the crystal structure. When you talk about atomic radius A between R, that table, you can know which one mechanism it can be used. If the R is small, then you use interstitial diffusion. If it is almost same, then we use substitutional. Okay. Second, temperature. So if the temperature have different, then diffusibility increase, like what you see on the screen here. I explained just now. Third one is the crystal structure of your solvent lattice. This one, crystal structure of your solvent lattice. So you compare the two, carbon and FCC, BCC. You see the value is different. FCC minus 15, BCC minus 12. So BCC is better to include carbon in the strengthening mechanism. Okay. So BCC, you already learned how to calculate atomic factor, packing factor, 0.68. FCC is 0.74. So if you look at the table FCC and BCC, BCC is 0.68, FCC is 0.74. You see the diffusibility value, right? So BCC will have higher value compared to FCC. BCC is 10 power 12 if you look at column 500 Celsius. And the FCC will be minus 15. Why? Because BCC have more space for you to fill in. Okay. Try to think how we ask you in the exam lah. Once you learn about this diffusion, then you expose to the calculation of atomic packing factor, then it can link with the strengthening mechanism later. Okay, we are now in a diffusion. Diffusion, the purpose of learning diffusion is for strengthening. Crystal imperfection that we learned previously is the defect that appear in a crystal. So if you have more boundaries or grain boundaries, then you have more space to fill in, then diffusion will be more easier to happen. Okay. Give you all and concentration just now. Concentration of diffusing species. Just now we talk about the flux. How the flux happen? Flux happen from high concentration into low concentration. So it depends on which one have high, which one have low. Then it tell you the direction. Okay. So this is another table. This is another table that you might help in your calculation. For example, diffusing species, host metal, or sometimes we will take out this name. We will take out this name. We will put solution and solute, or solvent and solute. We will not put this one because this is too direct. So normally we will modify a little bit on the labeling here. All right. And you have all the information. You have the DO, you have the Q value. Again, Q value, you have two column. One is in kilojoule, one is in EV. you need to be careful on the Boltzmann constant that you use. Boltzmann constant, you have two value, two different value. And calculated value temperature at 500, what is your D value? 900, what is your D value? Okay, so let's see how we apply this table, or how we ask you in the assessment. So you have a plate of ion, which is Fe, exposed to carburizing carbon rich, which is C, F and C now. So you have two elements. On one side, and decarburizing carbon deficiency atmosphere. So what does it mean? You have ferrum, you have carbon. One side is rich, one side is poor or low concentration. If the condition is steady state achieved, again, what is steady state? Steady state, you will see there is a drop of straight line on the curve, concentration and X. This one, C versus X, you see linear line. Calculate diffusion flux. This equation, J equal to minus D dC over dx. This is dC over dx actually is what? Is your gradient of your graph. Given in Celsius and Fahrenheit. What else? If concentration carbon given so and so, carbon at position of 5 and 10 mm is so and so. So you have two type of concentration at different location. We need the carbon sulfate are 1.2 and so on, respectively. Assume diffusion coefficient coefficient 3 point something. Okay, actually it's application of J equal to minus D dC dx. So this is the gradient again. Gradient, what you take? You take position A minus position B divided by X over A. So you should able to imagine the graph C versus X, and it's a stable condition. All right, I draw something on the whiteboard here. So A, B. So you have XA, you have XB. So you have concentration A, you have concentration B. All right. Information was given there. So CA is 1.2. Drop to 0.8. X is from 5 mm to 100 meter. Okay, sorry. The question have a wrong notation. Is -2, not 2. -2, So there's a question. There's a typo error in the question. It should be 10 power -3. The negative is missing in the question, and this is 10 minus 2. Okay. Then you substitute the value, you find the flux. The flux is positive. Okay, the flux is positive. 2.4 something. Unit must be correctly done in kilogram over meter square dot S. Okay, so this is how you do. It's quite direct. Direct. Yeah. Now, just now we deal with steady states. Now what happened to unsteady state? Unsteady state is that happen when the concentration of your solute at any point in material change with time take place. Where you will see in the beginning of lecture, there's a drop like that and not straight line. Okay, concentration drop in parabolic behavior in concentration versus X graph. So this is called non-steady diffusion. And you have the second equation for Fick's law. You use this one. Okay, so you have first Fick law. Just now is the first Fick law. Second Fick law is the one you see on the screen. You see the T. Second Fick law is focused on time, where you see there's a T there. So what you do, you take the T and you differentiate in time. Okay. So on the left is the rate of your C changes, your concentration change towards time. And this is the diffusion with a gradient. Huh? So we are not going to derive this equation, right? Some, they use partial differential. Partial differential means they will change this D into triangular D, a delta, but we'll just use the D. Huh? So some you use this symbol. Partial differential means very, very small changes. Right? Okay, so this is Ficker's second law during non-steady states. So what happened when you have a non-steady state? Again, non-steady state, we are focusing on time, and we like to freeze that time and study the condition. So let's consider a gas diffusing into solid B. Means this is a solid B. Gas A start to move into solid B, and there's a reference. The starting point we label as S0, and direction is go into solid B. So when you plot graph, at this moment you don't think of is this possible, and you pump gas into solid B. Try not to think first. Of course, you think of solid B as have a loss of hole one, and then pump in the gas. So for example, you pump in carbon dioxide into a carbon solid, for example, right? So you have a concentration versus X again. And initially, you have this time, T1, but there's a change of concentration when you change to, you have a T1 and T2, T1 and T2. So the curve, this one is T1, this one is T2. So when you see this not straight line one, is fall under non-linear graph, is under non-steady, then we will use solution of frequent loop. So derivation of this one here from the top to bottom, we are not going to show. It's not our area, but it will give you second frequent rules where you use CS minus CX, CS minus CO equal to ERF X 2 square root of dt. This is for non-linear. So yeah. So some textbook, they give you a condition. The same actually is the same equation. It's just that For example, the top one. The top one, you use CS minus CX. But the bottom one, it focus on your initial concentration, CO. Right? On the top one is it focus on the CS. The CS is the solid concentration. Bottom one is focused on the initial concentration. Both same, both give you the same answer. Both give you the same answer. It's just that different mathematic presentation only. Okay, you can prove lah, but we are not going to do that. So the second one, if you see 1 minus something, that is usually it used for semi-infinite solid. Some textbook, they use the bottom one. Our source, we use the top one. You can use the second one also if you want. Okay. So CS is a surface concentration. O is the initial uniform concentration. X is the one that you want to find. X is the concentration that you want to find at that particular time. Then you use the Fick's second law. Okay, you use the Fick's second law when you have a non-steady diffusion. Usually it's not straight line. It's a parabolic shape, right? Oh, there's all lah. Okay. X distance, diffusion, time. ERF is the function, is the error function. ERF, this one, there's a table for you to refer. It's like you learn statistic before, right? Now taking, okay. Or you take at max, right? Additional max. There is a book to refer. You still remember? Like a cos, cotangent, that one. Same. For this case, there is a table that is ERF. There's one table that's ERF. So same principle, like you find angle, then you refer to certain cost value and so on. Same. But now it's a ERF, it's an error function. I'll show you the table. This one. Exactly the same. So you have the Z, you have the ERF Z. So what you find is that we either give you Z, you find the ERF Z, meaning this is this one. This is this one. Okay, so you can use either one to solve this question. You know the concentration of surface, the concentration at the distance you want, Cx, the concentration, initial concentration that given in the question. What you need to master is the skill set to use this table. Okay, so there are steps to solve this kind of problem. So there are two ways we ask you. One, either we give you the Z, or we give you a condition of ERFZ. Then you find your Z. You need to do interpolation. Okay, you need to recall how to do interpolation. So meaning that sometimes your Z will be between, for example, I pick one value. For example, you'll get 0.588Z. 0.58Z. You need to find interpolation between this value and this value. That one is mathematics part already. If you don't know how to do interpolation, go home, ask Google how to do interpolation. Okay, let's apply this table. So you have a gas carburizing a gear. So you want to strengthening the rotating gear. You through a process called carburizing. So you expose the metals into a CO2 environment. So that process is called carburizing. The steel is 1020 at temperature 927 again. Do calculation in term of Kelvin. Change all the Celsius in Kelvin. Calculate the time in minutes necessary to increase the carbon content from 0.4%, 0.4% at 0.5 mm before the surface. Okay, so carbon content increased to 0.04. Assume carbon content at surface is 90%, 0.9%, and still have nominal carbon content 0.2%. Given your D value at 927 is 1.28 10 power negative 11 m squared over s. Normally, you call out this question. To be fair with you, when it comes to assessment, normally we'll say this is the non-linear or stable condition or non-stable state. So once you see the non-stable state, normally this is non-stable. Then you know that you use a second law, right? So CSO minus CX minus 1. Again, there are two equations you can use. Some you use 1 minus something. There are two form of equation you can use. You can use the top one or the bottom one. You will still get the same answer. Okay. So we call the equation. CS at the surface is 0.9. In the statement there, your surface CS is 0.9. CO initial is 0.2. Nominal carbon is given. Cx is the one that we want to find, 0.4. It increased to the target concentration, 0.4. The distance that we are looking at is 0.5 mm. Okay. So, and then the D value also given. So this one, basically, you have this one, this one, this one, this one. You have the X, you have the D. You are missing on time, right? Okay. So you need to change your unit into meter because the table that you're referring to, the Z value is in meter, unit SI. Remember to change into unit SI. Okay. Then only one is missing in the equation. So you calculate what is the value of this one. You substitute this value, all this value for your concentration, you get one ratio, right? Okay. You'll get 0.5 divided by 0.7. Your X divided by 2, you'll get 69.88. Of course, with the D value, square root D value, right? Square root D value, you'll get 69.88. Then you'll get 0.7 on the left-hand side. And then EFR is an error function, 69.88 over square root of T. Basically, you already can solve the question by referring to the table. This is ERFZ. This is the value of the ERF. So you let your Z equal to this one because you want to find the T later. We substitute this one as Z first because we want to use the table. So the equation changed from 0.7143 equal to ERF 69.88 over square root of T into the form that I show you on the screen. So this is what we want to find from the table, and you start to do interpolation. How? I'll show you the table. From the table, you have the Z row, Z column, and ER column. What do you understand about this highlighted 0.71 equal to ER of Z? Which column you are referring to? The left or the right? Right, yeah? So 0.7143, where does it fall into? Here. Here. Okay, 41, correct. About here. You put in 0.7143 here. This is your X. You do interpolation. You use this value, this value, this value, this value, and this value. So actually it's a 1, 2, 3, 4, 5, 5 value. So you do interpolation. You need to find the Z value here. Okay. So I pull into this one. So 0.7143 and the X value here. You need to do interpolation. So I show you the interpolation steps. You take 0.7143 minus the base value divided by 0.47 minus the base. Then you follow the row. 0.7143 is your X. 0.7112 is 0.75. And you follow the same for the bottom denominator. You rearrange the equation, you get your X. Okay? Can so during your test or final exam, don't panic. Don't panic. 69.88, you substitute. What is your X? Your X is 5.1, 10 power negative 4 divided by 2. And your D value is what? 1.28, 10 power negative 11. But this is square root number. You square root this number. You divide your X again. You'll get 69.88. This is, or you can multiply first if you want. Okay. But don't chase after the numbers. Just try to learn how to solve, how to apply the equation. That's more matter. Okay. So once you get your Z, your Z equal to 0.75, then you substitute back. What is your Z? Just now your Z is 69.88, right? Your Z is 69.8 over square root of T, right? So you use back the value, you rearrange the equation, you find your T. T with square root, you have a positive value and negative value. We take the positive value. The answer is 8567 seconds. The question asks you in, I think not mistaken, in hours and minutes. You change into hour and minutes. Okay, it's about 143 minutes. You divide by 60, you get minutes. Okay, the step of solving always the same. You write the equation of the second law of the Fick's equation. Then you replace the ERF x divided by 2 square root dt as z. Then you calculate the concentration that you have. You have one number. By using this solution, you go to the table, find the value of the ERF z. Then from there, you go back to find your z. The z is t. Okay, so since this is a tutorial question and already given to you, go back home, try to think. We will give you the ERF z value. Are you able to find the concentration that needed for that time? Here, CSZ. So this is one way, but how you do reverse? How if what happened if your CX, the concentration at that particular depth is missing? You want to find that concentration at that particular depth. How you find? Okay, so try to rehearsal this kind of question. Yeah. Okay, another example. Another example, so that one is one set. Now I give you second set question. We are still repeating the same step, same procedure. So look at the question. You are given same information. Is it the same? Let's see, oh, not same. Okay. So you are consider the same still in example 2. Example just now. Only this in this problem calculate the carbon content. It asks you the carbon content at that particular location. Like I once mentioned just now. Find the carbon X, the concentration at X. Beneath the surface after 5 hours of carburizing time. This equation, what is your T unit? Second. Change this time 5 hours to second. You find your this one. Assume carbon content so and so. Nominal was given, DC was given, X was given also. Basically, you can find your Z value. Okay, so same equation. You have all the C's, you don't know your CX. You substitute. You can either get one part of it again, change the hours into second. All right, basically you already have the value over here. All right, so you have 0.9 minus CX divided by 0.7. You have ERF value 0.521. So you have ERF 0.521. From the table, you can either find Z or you can find ERF. Right? So replace the constant value 0.52 as your Z. So let Z equal to 0.521. You go back to the table. You go back to the table. Okay, I speed up a bit. So basically, you go to the table. Your Z is 0.521. You go through the Z value. 0.521 is between 0.5 and 0.55. The value is here. You do interpolation to find the ERFZ value. You do interpolation. You find your X value or your ERFZ value is 0.538. Once you find your ERZ, you go back to the equation just now. Just now your equation is 0.9 minus CX divided by 0.7 equal to ERZ. So the X value you find from the interpolation actually is the right-hand side answer. So only one is missing. The CX is missing. Okay. The answer is 0.52%. Okay, so don't forget about the unit. The unit, if you write 0.52, it's not complete. It must have a percentage. So by this example 2, example 3 and 4, you should know how to flip the question, like how to do when you are given so and so. There must be something missing in that second law trig equation. Something will be missing. Okay. Polish your interpolation skill. Polish your interpolation skill. And don't press the long number during your assessment. Sometimes you know, but when you panic, you will press the wrong number, or especially the decimal place. You will forget the decimal place, or you press the wrong decimal place. Okay, the rest you read. So here it's just that you're comparing the result between example 3 and 4. You can see that when you increase the time from 2.4 hours to 5 hours, the carbon content below the surface increased from 0.4 to 0.52. You expose the metal to more carbon environment. the concentration on the surface will increase. Okay. Number 5, you go and read. I give you as your homework. You can read same procedure. I will not go deep. It's still the same. You just flip here and there. Huh? Still flip here and there, and find the interpolation value, and you answer the question. Okay. Example 5, you go and see. Okay. The rest is explanation on how you improve the things or more on the information for you. I go very fast. I just flip the slides for you. Industrial diffusion, where does we apply? This one, when you study how to do hardening later, or we call it strengthening mechanism in one of the chapter. You use diffusion for case hardening and impurity doping of a wafer. This one in the like Intel chip and so on, right? So you need these two, diffusion. So for example, all these things, and if you do the cross section, you see there's a different cross section, right? So outside one will become stronger because you need all this gear to be stronger. So you do diffusion process. Carburization, this one you go home and watch. It's just a chemical process. This one is how they do the silicon wafer. Also, you just go and read. And there's a video there. I think I show you this one. Okay. Then this one by experiment. Diffusibility given by this equation, right? And you go home and look at the tutorial question. So this is a diffusion also, but this one you need to use D equal to D not E power negative Q over R. Okay, D is a diffusibility. So you look at this example. It's a direct substitution. Okay, go and read. And you can write in a ln and log also, like previous the rate just now, same. So one on the top is ln, or bottom one is log. The rest you read. And there is a plot for the equation also. And this one is because you need to collect the data through experiment. So, and once you have the experiment data, basically you just direct substitution, you can get the answer, right? It is too simple, so sometimes we don't ask you in the test or final exam. Yeah. But this one will come up. Okay. So these are the plots and so on. You apply substitution, get the answer, right? Still the same, right? Read example 7, go and read. Yeah, read this one. Go and read. Okay. Example 9 is also one of the tough question. Might be in your final exam question. So you read how to apply the equation that we learned so far, right? It will link with the mechanical properties. Go and see how we solve this design problem. Okay, read how you do. There's a step-by-steps on finding the C constant, and then you solve the question. It's a this design question is combination between the second rules and also the diffusion equation just now. Okay, read now. Then you find the required answer, right? So these are the some of the sample question you can try out. With this, we conclude chapter 5. Okay.